Today, okay. Hey everyone, good day. So today we are gonna talk about a research paper titled like Altruistic Scheduling in Multi-Resource Clusters, or what the authors call Carbine. So this work is like done by Grandel Chowdhury, Akela, and Altanaran, and me along with my teammates Anish and Alchan will be taking you through what this paper does and like why it's interesting and how it fits into the landscape of like cluster scheduling. So cluster scheduling it is a big deal like in data centers. Like think huge clusters running massive jobs for analytics or like machine learning and just a ton of like different workloads. So the big question these schedulers try to solve is like how do we allocate resources like CPU or memory, disk, IO, and like network bandwidth to many competing jobs. So all of which we have different needs and dependencies in a fair and efficient way. So today we'll see how Carbine needs to Carbine tries to do something kind of radical. Let let jobs share resources they're not actively using to help others finish sooner, all without messing up like the fairness. That's the altruistic twist. So let's dive in. So let's start with some motivation, I guess. So first off, let's talk about why this is even a problem. Here, like modern cluster schedulers often focus on immediate objectives. So, and like ensuring instantaneous fairness. Fairness here usually means each active job or user gets a proportional share of resources. And this is done to prevent starvation or like to guarantee that no single job hogs everything, right? It's a great idea, right? So, but there's one uh, subtlety. Like these schedulers, by focusing on short-term goals, uh, miss out on potential long-term opportunities. In a large cluster, jobs have like complex structures and resource demands that vary over time. Sometimes, like a job doesn't need all the resources it's allocated at a given moment. So some tasks are waiting on others to complete, or like it's in a phase that's not so resource intensive, let's say. And like traditional schedulers don't really take advantage of these transient idle resources within a job allocation, and that can lead to inefficiencies where the cluster could have done more work if it had like redistributed the leftover resources, right? So for that, what do current schedulers do? Like the limitations we'll discuss about that here. Like so, let's say we have something like DRF, like dominant resource fairness, or even simpler multi-resource fairness solutions. They ensure like you get a fair share of CPU memory and etc. Uh, but they're kind of like myopic. If a job is allocated a chunk of resources, those resources sit locked to that job, even if the job isn't using them all at the exact moment. Meanwhile, other job might be like starving or waiting. The results is that while we maintain fairness in the short term, we fail to improve cluster utilization and average job completion times over the long haul. So schedulers like shortest job first or Tetris might optimize certain aspects like performance or packing efficiency, but these often can't guarantee fairness as strictly. There's this trade-off where like either we pick fairness at the cost of leaving some resources idle, or we pick performance but risk hurting the fairness. But here the authors of Carbine say like, wait, maybe we can get both fairness and better efficiency if we are a bit more clever about when we allocate resources. So, key observation from large-scale production traces like those at Microsoft is that jobs often have the slack in their resource usage. Let's say 20% of their allocated resources at some times aren't actually needed for that job to still finish on time. So if we could detect these leftover resources without harming the original job's completion, we could lend them to the other jobs, right? Yep, that's like the altruistic angle. So like you're helping others without hurting yourself. Over time, everyone benefits because when your job needs help, others might do the same for you, right? Yep. So take a look at this. So if you look at this figure in the paper, you can see how different schedulers compare on fairness, performance, and efficiency metrics. These schedulers cluster around certain trade-offs, but Carbine tries to break through by enabling these resources sharing and improving overall outcomes. So let's see about key questions we could be asking. So, uh, how like the questions could be like, how do we know which resources are truly left over and safe to reallocate? We must ensure that giving away some CPU cycles or memory now won't push the original job's completion out more like further. Also, how do we pick which other jobs to give these resources to? And should we pick the job closest to finishing or the one that has the biggest resource deficit? Like, and here, like for these, the carbine solution involves like careful scheduling at both inter-job and intra-job levels, like between the jobs and also within a single job's task. So the next slides will like detail how that happens. Let's see here. All right, the paper sets up the formal problem. Like we have a bunch of jobs represented as direct acrylic graphs, where each node is a task and edges represent dependencies. So each task demands multiple resources types like CPU memories and input-output networks, all these. We want to allocate cluster resources so that fairness, like no job is unfairly starved, and performance, it should be completing the job as soon as possible. And as for the efficiency, it shouldn't leave resources idle if they can do useful work. Uh, they show that even if we knew all future information, like for offline one, optimizing all these at once in NP complete, that means we can't find a perfect polynomial solution. But Carbine offers practical approach that gets close to even ideal behavior. So, yep, my friend Hanish will continue from now.
Now let's talk about altruistic scheduling concept. So what is altruistic scheduling? Practically speaking, suppose a job has a deadline or an expected completion time. If at some moment the job has more resources allocated than that needed to ensure it meets the target, we can just say, hey, let's lend these extra cycles, or memory to other job that's struggling. This lending is temporary and does not change the original job completion plan. Essentially, the original job is altruistic, uh, like it helps other job without any personal downside. Over time, as multiple jobs do this, the entire cluster runs more smoothly, and the concept builds the traditional idea of static allocations on its head, making them dynamic and cooperative. Uh, in this figure, we can see that it's a scenario between two DAGs share resources. Carbine identifies leftover resources from one and gives them to ask tasks from other job. They can be benefit right now, right not right now, boosting the job completion time and the cluster overall efficiency. In this slide, we'll talk about theoretical foundation. It's an offline case. In this offline world, a scenario where all n- jobs are known, their runtimes, and no new arrivals. The author proved that autism does not hurt completion times. This is a big deal because it established that under perfect information, being altruistic is always safe. Although real clusters are not offline, new jobs arrive unpredictably and gives a strong theoretical backbone to the approach. We talk about offline to online. In before slide, we talked about offline, right? Now we'll compare the both. We'll shift from offline to the online one. Now in real life, jobs show up at all sort of times. Task fail and restart. Resource demand are always known perfectly. Carbine deals with this uncertainty by continuously adjusting the allocations. It monitors the state of each job stack and recalculates when the task need to run to maintain that job ideal completion window. And then it frees up the slack resources for others. This continuous adaptation lets Carbine handle the dynamic conditions of a large production cluster. Now let's talk about inter-job scheduling. Inter-job scheduling basically asks like how do we split resources among different jobs running simultaneously. Many production clusters use something like DRF, which tries to ensure fair share. Carbine builds on top of these fair-based line schedulers. By doing so, it leverages the fairness logic to identify periods when a job allocated resources exceed than the job currently requires. So think of DRF fairness allocation as a starting point. Each job gets some CPU, memory, etc. Within that, Carbine finds times when a job task aren't running at full capacity. That's that's the leftover. Without changing their fairness guarantees, turbines reassign the leftover to other jobs. This approach means we don't lose the fairness that industry trust and rely upon. We add efficiency on the top. And intra-job scheduling is more local. It's about deciding which task within a single job should run now and which can wait. Carbine does a thing of backward scheduling approach. It means it look like the job DAX and the completion targets and figures out the minimum set of tasks that must run to stay on track. The tasks that are urgent, that don't need to run right this second, can be delayed slightly. Delaying these non-critical tasks free up resources. But importantly, this is a careful calculation where we don't just randomly postpone tasks. We pick those that won't cause any net slowdown. Essentially, we ensure the job end time isn't pushed out. That's how we guarantee the original job is not harmed by being generous. Now let's talk about leftover redistribution. Once we identify leftover resources, we redistribute them. The author suggests a shortest remaining time first SRTF strategy for those leftover slots. Why we use SRTF? Because by giving extra resources to the job that are close to finishing, we reduce their completion time faster. This also helps reduce the overall average JCT, which is often a key performance metric. In addition, we try to pack as many as waiting tasks as possible in these leftover slots, using them efficiently. So there are basically two goals. The first one is that help jobs finish sooner to reduce the average JCT. The second thing is that making sure that there is no resources goes wasted. It improves efficiency. Uh, Now, the properties of altruistic scheduling. Putting all these pieces together, Carbine ensures that it prevents and preserves fairness. No job gets cheated out of its fair share in the long run. It also ensures performance isolation. Like if a job expected to finish at time T, it will finish around T, as it uses all available resources so that the cluster is work conserving. All the properties mean Carbine meets the desired criteria. It's not just a hack, it's a well-rounded solution. Additional design considerations. Now, in real cluster environments, there are more subtitles, data locality. Like sometimes tasks prefer to run near their data to avoid network overhead. If we delay a task that would have run locally, we risk losing data locality. However, the author argued that often the gains from the leftover sharing overweight its potential local cost. After all, in large clusters, rerunning or waiting a bit might still pay off if we collectively finish jobs faster. Stackler migration. By prioritizing shorter or soon to complete tasks in leftover scheduling, Carbine can help tracking stragglers, those slow tracks that hold up a job, entire jobs of DAG. This reduces tail latency. Handling failures. If a task fails, Carbine just recalculates the complete estimates like PK values and adjusting accordingly. It doesn't treat failed tasks differently from new started tasks. Keep the logic and it keeps the logic consistent and robust. Now, my friend Aditya will continue the rest of the slides.
Thanks, Anish. So, all right. So now we'll head into the implementation part. So, how exactly do we implement this in a real system? So, the authors have built Carbine as an extension of two major components, Yarn and Tez. Yarn is widely used in a Hadoop ecosystem, and Tez is basically a DAG execution framework. So, they had to add some logic to the RPC, remote procedure call mechanism, which is basically how the resource manager talks to the application masters to share not just their fixed allocations, but all of their potential leftover distributions as well. It extends the existing RPC mechanisms to propagate the resource allocations between RMs and AMs. The TES AM is modified to use the intra job logic and figure out which tasks to run now and which tasks they have to delay so that they can have an easy scheduling pattern. So the thing is, it's not a total rewrite, but they do end up adding around 1400 lines of code. Uh, which when compared to a lot of large distributed systems, it's not really huge, but a very valid component. So this easily shows that Carbine can be integrated into all sorts of already existent cluster schedulers without making major overhaul or changes as such. So here's the architecture diagram of the integration. So these are the pieces that fit in entirely together. The job manager, resource manager, and the node manager working with its logic as highlighted over here. So it properly represents a multi-resource scheduling framework, which in a data parallel cluster likely aims at balancing efficiency and fairness in resource allocation. So the major lookout was to integrate framework in an altruistic and default scheduling strategy to optimize the resource usage across various nodes when we implement these architectures. So going in further into the architectural integration. So for major monolithic schedulers like Yarn, which have the resource manager and scheduling logic in a centralized manner, the jobs application master can implement altruism at the job level, and the resource manager manages leftover resources all throughout globally. For a two-level scheduler like Mesos, where a global master gives us the framework their shares, the leftover management might go entirely into a global master module. That's basically the difference between Yarn and Mesos in terms of this. So the main point in Carbine's concept is that it isn't entirely tied up to one particular cluster management approach. It can easily be applied to frameworks like Spark or MPI. So it gives us the flexibility and adaptability to even implement for all such resources and to have even for shared state schedulers like Omega. So yeah. So um, we'll start summarizing it. So basically, in a nutshell, uh, Carbine gives us the whole package of giving us intra-job altruism with uh, basic fairness, with leftover based redistribution, which is a major combination that we require. So by blending all of these together, it achieves a good sense of balance, giving us a good amount of pick in all these three options. So majorly without sacrificing fairness for efficiency, it keeps fairness while even still boosting performance and utilization. So it's a good way of layering altruism on top of all the standard policies that end up giving us one way or the other of giving a trade bias, whereas this is very standard. So the major highlights here are uh, the authors in this paper have modified Yarn's RPC so that the resource manager can pass on complete resource allocation into the AM, which then ends up deciding how to schedule tasks for altruistic giving. The test AM uses intra-job heuristics to determine which task can be postponed. So that's kind of the work of the scheduler as well. So the AM with Carbine logic figures out which tasks are critical and which can wait, which is basically what a scheduler does as well. But here the waiting part is being stressed on. So periodically, the cluster rechecks leftover resources and redistributes them so that there is effective balance even while maintaining fairness. So this process throughout, this iterative process ensures that the jobs run even while the conditions change. So Carbine continues to improve the cluster state, and it's a very dynamic process, and this is not a static one-time calculation. So right. So how do we show the evaluations and metrics? By the process of experiments, and the setup is the main part of it. So let's talk about the experiments. So they have tested Carbine on a 100 node cluster, each having around 20 cores, 128 GB of RAM and SSD. And they use benchmarks like TPCDS and TPCH. And they have majorly used Big Bench as well. So for support, they have used traces from Microsoft and Facebook with real production traces. So these traces individually represent thousands of machines and realistic workload conditions. So the main metrics that are valued over here are average job completion time. Uh, in general, how average time it takes for a job to get finished. Lesser the better. And make span, the total time taken for finishing a set of jobs. And Jane's fairness index, measure of how fair the resource distribution is. More or less, one is better, and lesser and lesser is worst. So let's say the goal is to reach one for a proper ideal fairness. So right, when we look at our major results, so Carbine basically matches DRF on fairness, which is more like a benchmark. But while even matching the fairness mechanism, it improves average JCT and efficiency significantly. So that's the main outcome that is needed for us. And through the process, they have reported about 1.2x times better efficiency and up to around 1.59x times of uh, lower average GCT in even some offline experiments. So even while keeping fairness in check, they have significantly improved all other parameters. This is exactly the big thing about the system, because there is no trade-off that is being done while just about nibbling at the edges. They are making significant and substantial improvements while not trading any part of the result. Right? So as we can see over here, without uh, much trade-off in the job performance, we can easily see the Carbine model outperforming other models in terms of fairness and cluster efficiency. So that's what we have been discussing about all along, and the graph perfectly depicts it. Uh, in general, other models have that trade-off. So that didn't stop over there. So, so the authors ended up testing what happens when resource demands are misestimated by as much as even 50%, so that to check how Carbine performs. And even then, Carbine still outperformed DRF and Tetris, which are again benchmarks for such systems. So uh, for checking scenarios like scalability, they ended up scaling the system by increasing the altruism in about thousands of nodes, and found out that Carbine still continues to help as the cluster size improves and the complexity grows. So as far as scalability is concerned, it's a very good boost when the system size enlarges and the system keeps performing well. So, so as far as the results go, One example, one figure might show how the performance improves even under high load conditions, or how increasing the probability of altruism yields bigger benefits. So others end up show how using a more advanced intra-DAG scheduler like DAGPS or Carbine's leftover strategy can further boost gains. This basically proves that the Carbine's idea of altruism is a fundamental concept that can stack with other optimizations. So here, also by prioritizing the shortest remaining time tasks, they entirely reduce the tail latency significantly. So instead of just improving the mean metrics, they ensure that the fewest of jobs get stuck as outliers. So this ends up addressing a common problem in large clusters where few strangler tasks dictate overall completion times, where small, minute outliers end up taking up too much time in a bigger picture. So this again proves us one of the major improvements and advantages of such a system. And going back to Shiv for the conclusions and the end part.
Right. Thank you, Arjun. And so for conclusions, so let's see. So from all this, what's the takeaway? That's what we're going to discuss. So Carbine, uh, I think you guys, like everyone understood, like Carbine challenges the status quo of like cluster scheduling by saying, let's say like, look, don't just stare at short-term fairness. Try a more long-term perspective where jobs can be altruistic, temporary giving up resources they are not using right now to help others finish sooner. Sounds good, right? Right. So this approach doesn't require sacrificing fairness. So, and jobs still get their fair share over the long run, but it uses every resource more efficiently, improving the efficiency and in turn reduces overall job completion times. So, and like this combination of fairness, efficiency, and performance is something schedulers have struggling for like long time. But here, Carbine shows we can do better than the traditional trade-offs by introducing like a bit of altruism into the system. So let's see some critics. Uh, yeah, like before we wrap up, like let's be a bit critical about this. The paper is quite strong. So it's novel and well grounded in theory. So implemented in like also like real frameworks and tested against realistic workloads. The improvements are like very notable. But however, there are some downsides or at least complexities. Excuse me. So it's more complex to like implement than a straightforward like DRF approach. And like operators need to trust this new logic. And the other point is like data locality can suffer if tasks are delayed at inopportune times, and the authors don't fully quantify every possible edge case here. Also, the ideal benefits like might depend on the accuracy of like completion time estimates. If those estimates are off significantly, like we might not always see perfect results. Still, considering all that, the authors managed to show a significant improvement. That's not just incremental, but conceptually different, like introducing altruism as a new dimension. So it's not just a small tweak, it's a new way of thinking about like leftover resources. I think everyone just understood what it tried to say there. And like overall, like I think the author succeeded in demonstrating that fairness, efficiency improvements, uh, these are not mutually exclusive if you approach the problem from this altruistic perspective. And that's basically it. We have seen what carbine is, how it identifies like leftover resources, redistributes them without like extending like completion times, how it integrates with frameworks like Yarn and Tez, and how it outperforms conventional schedulers like in expensive evaluations. Yeah, that's for the paper. So thank you for your time, guys, and I'm happy to discuss any questions you might have.
Thank you.
Thank you.